the Telcoin Network protocol. We're going to be looking at the Rust portion in this video. So the main entry point for the Rust code is in this binary Telcoin Network. This contains the logic for the actual main binary. And I want to bring some special attention to here because this is really a critical portion of the code where we are retrieving the BLS passphrase to decrypt the secret key for validators to sign votes on consensus messages. And this is the main entry point on how that is loaded into the program on startup. Validator nodes use the BLS keys to sign votes, and they also use ED25519 keys to sign network messages. The BLS key is maintained and pinned in memory and not exposed. The network key is passed to the libp2p network portion to run those behaviors. Inside the binary, basically the main entry point for running a node is going to hit this node subcommand where we have a lot of the arguments here. And then ultimately at the bottom, we will launch the node. This launcher can be found inside of our main crates, libraries, the node, and right in here. So this library it creates the runtime. It also creates the epic manager, which is sort of the main task manager for the entire node. And once that is initialized, we're just calling run. So run is located inside this manager once it's initialized. And this is the core logic for the node. Nodes run nodes run for the lifetime of the node, the entire process, but epics only run for certain periods of time. After the epic boundary is reached, the node will shut down certain tasks related to the epic while preserving other tasks that are related to the operation of the node. Things that survive epic boundaries are the engine, which executes consensus transactions and extend the canonical tip. This is executed through the EVM. But the primary and worker, which reach consensus, these are part of the epic tasks that shut down at the epic boundary. So another task that survives epics is the network portion. So on startup, the node will reach out and try to discover peers. This is a network request. Our main network implementation is in this crate network libp2p. And consensus RS will have a sort of generic networking type for libp2p compatibility that is used by both the primaries and the workers. The primary and the worker have independent networks because primary only talks to other primaries, and a primary talks to its own workers. Workers only talk to other workers, and workers also talk to their own primary. So this sort of horizontally scales out some of the workload for the protocol because workers are responsible for creating batches of transactions and validating it with their peers. Once the batch of transactions is validated, the worker sends it to its primary. That primary will then include it in its next header. That header will only include the digest of the batch that the worker has validated with its peers. And when the primary proposes its header, which again, the payload for the primary header is just digests of batches to keep the message size small and efficient. When primaries are validating other peers' proposed headers, they ask their workers, have you seen this batch? Have you validated this batch? And if they have, then that primary will proceed to validate other aspects of the primary's header. Once that header is fully validated, the node will vote for it. With enough votes to reach a quorum of 2f+1, which is more than 2/3 of the committee have voted in favor of a header, that primary will create a certificate. And the certificate holds the header information inside of it. It also holds the BLS signatures from all of the nodes that voted in favor of that certificate, which can then be further verified by other peers before accepting that certificate. Once you have enough certificates from the previous round, the round will advance. And that is the idea behind Narwhal and Bullshark, which is our consensus logic. But back to the networking code here, we have several important behaviors. These are used by both the worker and primary networks. Again, they share the same sort of network structure. Identify is used to confirm external addresses seen by peers. Our gossip sub gossips out events such as a batch digest that was created so that nodes can download it. It also will gossip out smaller messages such as certificates, which are expected to be at the most 18 kilobytes in size. The request response behavior is used for direct peer-to-peer communication. It's basically an RPC server. The peer manager has a lot of responsibility for this implementation. The peer manager is a custom behavior that is not provided by libp2p library, and it is the main connectivity manager for the network. The peer manager keeps tracks of peers, their status, their connection status. It also issues dial requests, and it keeps track of scores for peers. So when messages are passed to the application layer, let's say we receive a request from another primary that gets passed on to the primaries, the primary crate and consensus here. If the primary has any issues with that message, it will report a penalty for that peer that is then handled by the peer manager. With enough penalties and a low enough score, the peer manager will issue a disconnect for that peer. Another thing that the peer manager is responsible for is to keep track of the number of nodes that are connected. And if there's too many nodes that are connected, then you can have a disconnect with peer exchange. And so what the peer manager will do is it accepts the connection incoming. It will see that there's too many peers here, and then it will issue a disconnect, but it will also exchange peer information to help that node that was trying to join the network hopefully discover other peers. So that, again, a lot of that logic is in this peers thing. Really in the behavior, you can see like handling pending inbound connections, the established inbound connections, and then the disconnect peer exchange is also part of the in this poll here. So that's kind of how the discovery works for Telcoin Network at this time. Jumping back into here. So other than that, this is really just once the network starts, you can see we have some we pass in some configurations, and then we just run an event loop. And this where are we? Here we go. This is the main method for running the loop. We're just selecting events from the swarm, or we receive commands from network handles. All right. Outside of the network, I just want to run through the main flow. So workers produce batches independently of one another, so transactions are not gossiped before consensus. And so that kind of presents a couple challenges. Workers don't know if there are duplicate transactions in another worker's batch. There could be nonce issues, but from the worker's perspective, when it creates this batch of transactions, those transactions are always built off of the canonical tip of the finalized header of the EVM. So primaries reach consensus. The consensus will, through Bullshark, creates a sub-DAG. That sub-DAG is committed, and then that output is sent to the engine. And the engine is responsible for basically building the payload here. So workers do not produce empty batches. So if there are no batches in a sub-DAG, then they will be empty. This is the logic for handling that payload. Otherwise, in mainnet and in an ideal happy path, we have lots of batches of transactions that are looped through to create payloads, and then they're executed one at a time. This execution is where the EVM is involved, and the block context for the EVM is one-to-one block to batch. And so with that, this execute payload, a lot of that logic is located inside of our Wreath abstraction here. We're using Wreath for, some people call it Reth. We're using this library for our EVM compatibility. Our main function in here for building these blocks is build block from batch payload. You can see this is kind of where we're initializing the EVM. We're looping through these transactions, and then we finish off with the builder outcome to produce the executed block with the try updates. Oops, this one. And that's ultimately what gets stored into the database. And this is the part that a lot of EVM developers are familiar with, right? This is how we turn our consensus blocks into EVM blocks. Some important areas in this crate besides this library, a lot of this is sort of compatibility stuff, but the system calls is where we have our interface between our smart contracts. So the consensus registry abstraction is in here, and that's pretty much the only abstraction we have for now because everything goes through the consensus registry. But this Sol macro creates these methods for us, and they're ultimately used in our EVM abstraction. So the two important places to start for EVM is inside of the mod RS here. You can see down below, this is where logic for like transact system call is, where we're creating the transaction environment. We're actually calling transact on the transaction to go through the EVM. We have a custom handler as well that is responsible for a different approach to handling base fees. And that is that instead of burning base fees, they are sent to the consensus, the governance contract rather, for distribution and management off-chain. Block RS is another important module for inside EVM because this is where at the end of each epoch we have two important calls. We apply consensus block rewards for the entire epoch, and we apply closing epoch contract call. Now that must be in that order. We always apply block rewards first, and then we close the epoch contract call. And that's when the smart contract logic is invoked for consensus registry and the state config, etc. I guess a little bit of background on this approach too is that for anyone who's not as familiar with Narwhal or Bullshark, the idea is that you have local DAGs that are produced on each node deterministically. And so once these nodes reach consensus and they're able to commit a subdag can produce a struct that contains a lot of certificates, and each certificate can contain a lot of batches, and a batch contains a lot of transactions. And so all of these kind of go through the system where once the subdag is committed, we flatten of all the batches, and a batch is executed one at a time per block. The EVM handles duplicate transactions and that sort of thing because at this time that's considered an acceptable inefficiency. But it should not cause or disrupt problems. In the worst case scenario, we produce identical batches across all nodes of the network, and ultimately we would have several batches in that subdag that contain the same transactions. We would produce the first EVM block that contained all the transactions, and then it would produce one block for the remaining batches, but none of the transactions would be included because they would all be ignored during execution. For a specific payload logic, this is where that's going on. But yeah, this is sort of any sort of EVM logic is really isolated to just T and Wreath in this crate. Let's see. Okay. Other than that, I guess just a few more tips and suggestions. You have the batch builder. This is the logic for how a worker collects transactions and builds its batch. Then you have a batch validator. This is the logic that the worker uses to validate batches from peers. Our configuration here is, I would appreciate some attention to this as well. This is all pretty important. We have our network configurations here where we have timeouts and peer score logic, etc. Anything to do with configuring the libp2p implementation is located in this configuration. We also have our Genesis configuration where we are pre-executing some transactions that are needed, such as initializing the first committees in Genesis before we start the node. But the keys config is probably the most critical from a security perspective. This is the one that really contains the key pairs for the, again, the primary key pair, which is the BLS 12381, and then the network key pairs, which is just an alias for the identity key pair. But again, we're using ED25519, so these are just wrappers. The way that we derive the ED25519 key is a little bit unusual. So the BLS keys are generated randomly for the validator in the CLI key tool here for generate. But once these the BLS keys are generated, we are generating the network keys based on a passphrase that the node operator passes and is signed by the BLS key pair, and that's the source of randomness to generate the ED25519 key pair. So as long as that BLS signature is treated like a password, and it's, you know, the node doesn't sign a BLS like a message with its BLS key that would basically be the seed used to create the network key pair, then we believe that that's a secure approach. Again, consensus has a lot of the primary and worker consensus logic for message passing. So the worker produces batches, they're validated, it gets sent to the primary. The primary proposes headers. Once they're validated, it creates a certificate. Once there's enough certificates, the round advances. Once the round advances enough times, then it's able to commit to the subdag. And those committed subdags end up in the executor for the subscriber. And this subscriber is responsible for just receiving output from consensus and forwarding it to the engine. That's really its only job. When the output is sent to the engine, the Epic manager here actually will check that the Epic boundary hasn't been reached. It'll check that output in the wait for Epic boundary. So if the output right now we're based on timestamps, this could actually change to be block height if the number of consensus blocks are produced a certain amount. But if this time is reached, then this is when the Epic manager decides to go ahead and begin the process of shutting down tasks for consensus. To start shutting down consensus to roll over the Epic. And when consensus starts and the new primary and the new workers start up, it's really kind of conceptually, you can conceive of it as like a whole new genesis for consensus. There's no historic certificates, there's no historic committees involved with consensus. Each time the primary and worker restart at an Epic boundary, it's as if from their perspective it's brand new. The only information and data that rolls over is with the engine and the executed EVM block from the canonical tip. Because of the nature of Bullshark and the local DAG commits, once a block is produced in the EVM, it is impossible to reorganize. There's no forks, no branches in our EVM tree. Okay, kind of moving on down, some other helpful insight. The state sync is really useful for determining the type of node that is involved. So if there is a committee validator, that is a committee voting validator would be in the current committee for the current Epic, and they're voting on consensus. The other types of nodes would be an observer node, which is could be a staked validator that's not a part of the committee, or it could just be a different node that's just interested in independently executing transactions. But the observer nodes just subscribe to consensus output and they execute transactions independently. All execution results are, there's a slight delay, but they are included in the next header for the primary, and so they are validated at that time. If for whatever reason there was a fork, then the primary would not be able to have its header, its proposed header would not reach certification, and once enough committee members fork, they can no longer reach consensus, and the network would stop. Storage has a lot of our database implementations. We covered TN-Wreath. TN-Utils is just kind of like a couple like synchronous library tools. Our TN-Types holds most of our types for everything. So we have a crypto library in here that manages a lot of the wrappers around the key pairs. The types for the primary might be interested if you're looking. So you can see out what the actual. This is the consensus output that gets passed to the engine. This contains all the information from the consensus layer that is needed for executing all the blocks for that final round of consensus, or that committed round of consensus. This is the header that is proposed. You have the certificate that contains the signatures for the committee that approved the header that was contained in this certificate. And then, very similar to Ethereum, we also have the concept of like two parallel chains. This is the chain that is used. This is the header that extends the canonical consensus chain, and then we have the familiar EVM headers that extend the execution chain. Let's see. So, other than that, I think that kind of covers like the main libraries for the repo. If there's any follow-up questions, please feel free to reach out on Discord, and then through the Cantina page, where we want to support you guys to find as much findings as you can. As far as providing proof of concept and test results, I think what we're trying to be as lenient as possible. Where if it's a very obvious issue, then we're not forcing that a proof of concept test to be issued. But if it is more complicated, or if it's a little bit less obvious, we would really appreciate a proof of concept test with your finding that just help us fully understand what it is that you've discovered as quickly as possible. And in order to do that, you might find our test utilities helpful. This contains some tools so that you can create like an entire committee with all authorities in the committee. And with this authority fixture, you'll have access to their private keys, so you can sign actual messages, etc. If you need any sort of access to the execution environment or the EVM database, you can use a default test execution node. Now, these are sort of high-level abstractions for the entire node. If you need anything more specific, a lot of the libraries contain test utilities with a feature flag. There are examples throughout the code base. I think down here we have some tests for, this would be a unit test to just kind of for validators and conclude epic call. And then another testing resource for you would be in our binary Telcoin network. In this tests IT directory, we have a lot of end-to-end tests here. This is our epic boundary. This would be a full end-to-end test where we're spawning 5 nodes in the initial committee. We issue an NFT to a 6th node. It stakes, it activates, and it goes through the process of joining the committee and being shuffled into the committee as the epics rotate. That would be this test. Faucet is used for testnet, so please ignore any faucet test in this code base. It is out of scope for the competition. It's only used in our DevNet right now. Genesis tests has a lot of the logic where we're testing kind of that pre-execution so that we can get the correct information into Genesis before we start the blockchain at Genesis. And then our restart tests are some of our hardest tests on the network, where we are shutting nodes down. They're sitting outside of the garbage collection window, which forces a committee node to resync, to rejoin the committee. There's some other tests too where it's like just random shutdowns and trying to recover. So that's a lot in these restart tests. So I think that is it. The last thing that I want to do is for any developers that want to run a local test script. We have inside of our etc. file here, we have two approaches to run a local test net. That could be in our shell, our bash script here for local test net. Now this is sort of the initial commands here. If you need to pass start if you want the network to start, you have to pass in dev funds to fund some address. The terminal will prompt you if you're missing any information, but this network is designed where you can just create validator keys without passing in start, and you can see in your local validators all the protocol information that's produced. Here's the node information for validator 1, for instance. Yeah, and so inside this local testnet script, you can also, at the bottom here, this is where we're actually starting nodes, and this would be where you could pass in Rust log information. We do use the tracing library, so you can go through and find any infos or debugs. We have some traces as well for that nitty-gritty granular logging. And then this local testnet does also start an observer node. So for those that are more interested in just running a Docker, we have a compose YAML here that is set up. If you want to, so just the basic make up, make down commands, but or the Docker up, yeah. I'm used to using make file, so we have our two helper commands here. You should just be able to get the network up and running by calling make up and make down. If you don't want to build every time, you can take that step out, but it may not be helpful because our code is frozen. But if you're changing things and you want to see that change in there, the default is it will build each time. The other place that you would probably need to change is in this context right here, that just basically creates the image once and uses it throughout the Genesis commands, and then at the very end we start the nodes for validator 1, 2, 3, 4. The ports are available 8545, 8544, then they just go down for the 4 validator nodes for this committee. Okay. Last thing I can think of that I'd like to pass on, again on the make file, we've included the contracts repo as a submodule. This is also in scope for the competition. If you're having trouble running Telcoin Network binary, you may need to initialize the submodules. We have a make command for that, or you can just run git submodule update. We don't have any recursive contracts in here. This is just more or less of a future-proof approach. But once you do that, you will have the TN contracts repo populated. A lot of these contracts are pulled in for the Sol macros and to interact and put into Genesis. So you need to initialize this submodule before the repo will work. All right, well, I think that is it. If you guys have any questions, please feel free to reach out. Again, we're more than happy to support you in your research, and we're really looking forward to the findings you produce. Thank you for your time.